Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay, so this is the 13th lecture of CSIR Net Physics 2021 paper solution. Okay, so this is the 13th part of the series of CSIR Net Physics 2021 paper solution. Okay, and also guys, before starting the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science, and also share my lecture details with your friends so that they will also be able to watch my free live lectures and will be benefited from it. Okay, so let's get started. Okay, so my class was ended automatically yesterday and I was solving one question, that part C question, and class was ended. So I'm starting with that question. Okay, and I apologize for the inconvenience. Okay, so let's get started. So that question was related to, so that question was from electrodynamics. Okay, so question is, the figure below shows, I have explained this question in my previous class, you can check that. Okay, I'm writing the question quickly. The figure below, so I'm not going to write the question, okay, because that I have already written uh, in my previous lecture, so you can check from there. So I was solving that question and that time my class was ended. So I'll make a figure and directly I'll solve it. For question, I would request you please watch my previous lecture. Okay. So the figure was, so there was a capacitor, okay, whose plates are circular. And the radius of circular plates are R. Okay, there is point P1, okay, and there is point P2 which is outside the capacitor, okay, and the transversal distance of P1 and P2 from the line joining the centers of the circular plates is R1. This is R1. Okay, so this is the transverse distance of P1 P2 uh, from the capacitor. Okay, from the line joining the centers of the capacitor. Okay, and also there are 2 points. This point is P4. Okay, and this point is P3. This is inside the capacitor. Okay, so these are this was the question. Okay, so what we have to find out is we have to, we have to find the magnetic field at this point, this point, this point, and this point, and then we need to find the relation. Okay, options were given there. Okay, please check my previous lecture. This one. Okay, and this is the distance of P3 and P4 is R2. Okay, from this line joining the centers of the circular plates of capacitor, this distance is R2. This distance is R2. This distance is R2. Okay, so transverse distance of P3 and P4 is R2. So that is what is given in question, and I have explained question properly in my previous lecture. I would suggest you please check my that lecture. Okay, and options also I have written there. Okay, so now I'm going to solve it, guys. So what I'm going to do is I will find magnetic field at this point, P1 at P2, P3, P4, and then then we need to find the relation. Okay, and after that we need to select the correct option. Relation between B1, B2, B3, and B4. So magnetic field at P1, I'm calling it at B1. Magnetic field at P2, I'm calling it as B2. Magnetic field at P3, B3, and magnetic field at P4, B4. I'm calling. Okay. Okay, guys. Meanwhile, just let me check whether I'm audible or not, so that I'll proceed further. P1 at P2, P. Yes, I'm audible, so I'll proceed further. Okay. Okay. So I'm solving now. So guys, magnetic field at P4, P4 and P2 will be, we can find the P2 and P4 using Ampere's law, because these points are outside the capacitor. Okay. Okay, so I'll write it. Magnetic field at magnetic field at P, P2 and P4, P2 and P4, okay, P2 and P4, P2 and P4 can be simply, can be simply, can be simply written, written using, written using Ampere's law, Ampere's law, as these points are, these points, these points are outside the capacitor, outside the, outside the capacitor, outside the capacitor. So we can see P2 and P4 are outside the capacitor. This is the capacitor. Okay, made of circular plates of radius r. Okay, outside the capacitor. Therefore, therefore, magnetic field only depends. Therefore, magnetic field only depends upon, only depends upon, only depends upon the magnitude of the magnitude, the magnitude of, the magnitude of free current, magnitude of free current, magnitude of free current, which is just I. Okay, this one. Okay, so magnetic field at P2, P4 can be simply written using Ampere's law. As we can see, these points are outside the capacitor, right? Therefore, the magnetic field only depends upon the magnitude of free current, which is I. Okay, so free current is I. Okay, so now we can easily find out magnetic field at P2 and P4. So at P2, that is magnetic field, we can write at P2 magnetic field I'm writing as B2. Okay, so B2, which is function of R. Okay, B2 is going to be this one, normal mu 0 I, because I is free current. Okay, mu 0 I upon 2 pi R1, 2 pi R1, because this is the R1 is the transverse distance from the capacitor. Okay, so P2 distance, this distance is the distance from the line joining line joining the center of the capacitor. Okay, so this distance is R1, 2 pi R1. Okay, and similarly P4, I mean to say B4, which is function of R, that is going to be mu 0 I upon 2 pi R2. This one, mu 0 I upon 2 pi R2, because this R2 is the transverse distance from capacitor to that P point P4, right? P4, or the distance of P4 from the line joining the centers of capacitor. Okay, so these at these point, because these 2 points are outside the capacitor, so we have found magnetic field easily, right? This is 2 pi mu 0 I upon 2 pi R1, and at this point mu 0 I upon 2 pi R2. Now we'll find magnetic field at P1 and P2. P2 is also in the range of this one, right? A capacitor. Okay, now magnetic field at P1. Okay, magnetic field at P1 means at this point. So this is going to be, we'll use this formula, guys, very important formula you need to note down. Integration B dot dl, integration B dot dl. Okay, integration B dot dl equal to mu 0 I enclosed, plus mu 0 epsilon 0 surface integration dE, mu 0 epsilon 0 surface integration d upon dt. Okay, d upon dt and dA dot dA means area, right? dA dot dA or ds we can write dA. Okay, so this is very important formula, guys, you need to note down. Okay, so we'll use this formula at P1 and P3. Okay, because these points are in the range of capacitor, within the capacitor. Okay, so this is in integration B dot dl equal to mu 0 I enclosed plus mu 0 epsilon 0 surface integration dE upon dt dot dA. Okay, A is the area vector. Okay, so now the conduction current is 0, since the conduction current is 0. Conduction current is 0. Conduction current is 0. Further note that the displacement current so conduction current is 0. Further note that the displacement current doesn't flow outside the plate, doesn't flow outside. Okay, so displacement current doesn't flow outside the plates. Outside the plates. Outside the plates. Therefore, therefore, R equal to R. R equal to R on RSS on right hand side. Okay, on R equal to capital R on right hand side, and R equal to R1 on left hand side. This you need to understand. Here you can see this radius or plate is R, right? So this, if you talk about displacement current that flows inside the capacitor, right? So this displacement current flows inside the plates, right? So in so that's why for displacement current, so we can see here this one displacement current. So displacement current doesn't flow outside the plates. Okay, so therefore R equal to R displacement current, guys. Current. Okay, so displacement current doesn't flow outside the plates. Therefore R equal to R on right hand side and R equal to R1 on left hand side. So here we need to find out. So we'll use this formula. This is left hand side. This is right hand side, right? So this is going to be 0 because conduction current is 0. Here displacement current will flow inside the plate, right? So that's why we will take R equal to uh, small r equal to capital R here, which is the radius of circular plate, and here we are going to take R equal to R1, right, in left hand side, because this is R1 is this distance, guys, transverse distance. So now we'll use the formula. So this is going to be, in this formula, this is going to be B, left hand side is going to be B1 into 2 pi R1. Okay, we have taken R equal to R1 at right hand side because this is the point. Okay, and if you talk about displacement current which flows inside the plate, so that's why we'll take R equal to R for displacement current. Okay, so this is going to this value is going to be 0 because conduction current is 0 plus mu 0 epsilon 0, and here you need to understand this. Okay, so this is going to be this one integration. This is going to be d upon dt and DE value, right? E is going to be sigma upon epsilon 0, right? Because we know that electric field inside the capacitor, between the capacitor, is epsilon 0, E upon epsilon 0, right? So this one, sigma upon epsilon 0, right? Sigma is the charge density. So electric field is sigma upon epsilon 0 in the within the inside the parallel plate capacitor, we know, right? So this is sigma upon epsilon 0, and now this value is going to be this one, and this integration, because we will take R equal to capital R, right, inside the plate. So this is going to be surface integration dA equal to, that is pi r square. This is going to be the area, right? Pi r square. Very simple one. This is b1 into 2 pi r1. R1 is transverse distance. This value is going to be 0, and this is mu0 epsilon 0. E value we know, right? For parallel plate capacitor, E value is sigma upon epsilon 0. So we have put the value, okay. And this area is dA. Surface integration dA means that is area, total area. So here because current flows, displacement current flows inside the plates, right? So that's why this is pi r square. R will be R, okay, pi r square. This is the area. I hope you have understood it. Now I'll simplify it further. So this is going to be mu0 epsilon 0. So now b1 into 2 pi r1 equal to mu0 epsilon 0. Here you need to understand, this is constant, this will come outside, okay, upon epsilon 0, okay, and this is now going to be this one, d upon dt sigma into pi r square, right? So b1 into 2 pi r1, b1 into 2 pi r1, b1 into 2 pi r1, that is going to be equal to this one. This is going to be mu0, okay, this will get cancelled, okay, mu0 into dq upon dt, because we know that sigma equal to charge per unit, this one, right? Charge per unit area, that this is the charge density, right? So from here q value is going to be sigma into pi r square, right? Sigma into pi r square. Since we know, right? So sigma into pi r square, that is q, dq upon dt is I, right? So b1 into 2 pi r1, that is going to be mu0 dq, we'll write mu0 I, okay, mu0 I, current due to mu0 I, okay. So this is mu0 I, guys. So from here we can get b1 value. B1 value is going to be mu0 I upon 2 pi r1, okay. So this is the b1, this is b1. Now we'll find magnetic field at this one, magnetic field at b3, this one, magnetic field at p3, okay. This point, at this point we are going to get magnetic. So this is inside the capacitor, okay. So magnetic field at p3, okay. So again we'll use the same formula, okay. This is this one, I'm writing in red, okay. Integration b dot dl, integration b dot dl is going to be equal to mu0 I in enclosed, mu 0 I enclosed, mu 0 I enclosed, okay, mu 0 I enclosed plus mu 0 okay, so mu 0 epsilon 0 integration surface integration dE upon dt dot dA. Right? This formula we are going to use it. So again, so this is going to be that B3 into 2 pi R2, this one guys, okay, this one. So at this point we are going to get, so transverse distance to B3 into 2 pi R2. Transfer distance is the distance of this point from the line joining the centers of the capacitor, this one R2, right? This one R2, R2, and that is going to be equal to mu 0 epsilon 0, mu 0 epsilon 0 d upon dt, and E value we know, right? E value we know, that is sigma upon epsilon, sigma upon epsilon 0, like that this one, the magnetic field, that this one electric field at the in between the capacitor, right? Between the plates of capacitor, this we know. So since we know here E equal to sigma upon epsilon 0, okay. So sigma upon epsilon 0 into this is going to be d, surface integral dA means pi r2 square, pi r2 square, okay, pi r2 square. Here you can see, I'll show you at this point pi r2 square, because r is, capital R is greater than this r2, okay. So at this point this is between the plates, right, plates of the capacitor. So at this point this is going to be this is going to be pi r2 square, okay. Okay, so pi r2 square. So we'll simplify it further. So this is going to be b3 into 2 pi r2, that is going to be mu 0 epsilon 0, we can take epsilon 0 outside, right, d upon dt, this is going to be sigma into pi r2 square, right, sigma into pi r2 square. This epsilon 0 will get cancelled, okay. And here we can, what we can do is we can write mu 0 epsilon 0, okay, mu 0 epsilon 0, and this is we can d upon dt sigma into pi r square, we can multiply this by pi this r square into, and we can divide it by pi r square, pi r square. pi r square. Okay, so this is going to be, this value is going to be sigma pi pi r square is q, right? So mu 0 epsilon 0 this is dq upon dt is I into pi will get cancelled. Okay, so this is going to be r2 square upon r square, r2 square upon r square. Okay, this value, this one. So this is b3 into 2 pi r2. Okay, now so from here b3 value will find out, b3 value. So this b3 value is going to be, this will go this side, right? So this is going to be r2 will get cancelled, this r2 square. So this value is going to be mu 0 I r2, this epsilon 0 is cancelled, right? So mu 0 I r2 upon 2 pi r square, 2 pi r square, this one. Okay, so r2 will get cancelled, this 2 pi r square, right? 2 pi r square, 2 pi r square. Okay, so this is value of b3. Now we'll compare these three. Okay, so look at this b, this one. b2 value is this, b4 value is this. Okay, and b1 value is this, and b3 value is this. Okay, so from here we can see that this one b1 equal to b2, we can see. So you look at the b1 is this mu 0 I upon 2 pi r1, and this b2 is also mu 0 I upon 2 pi r1. Okay, so it means, and if you talk about this one, so we can see, since b1 equal to b2, we have found. Okay, b1 equal to b2 we have found. So b1 equal to b2. Okay, next is if we talk about b3 and b4, so what we can do is, for getting relation, we can do b3 upon b4. Okay, so b3 value is this mu 0 I r2 upon 2 pi r square. Okay, 2 pi r square into upon, and b4 value we have got, the b4 value is this one mu 0 upon 2 pi r2, right? Mu 0 upon mu 0 I upon 2 pi r2, 2 pi r2. Okay, so if we solve it, we are going to get this value, everything will get cancelled, so we are going to get r2 square upon r1 square, r2 square upon r1 square. Oh, my apologies, it's r square, r2 square upon r square. And we know we know that this R2 is greater than R is greater than R2, right? Here you can see in the figure, this one. R2 is less than this R, right? Radius of circular plates of capacitor. So it means this value, this is greater, means this value is going to be less than 1, or we can write that implies V3 upon V4. I'll write in next page. V3 upon V4 V3 upon V4 less than 1. Okay, that implies V3 is less than V4. So what relation we have got? We have got B1 equal to B3, sorry, B1 equal to B2, B1 equal to B2, and B3 and B3 is less than B4. So this is the relation we have got. Okay. So which option is matching? You can check option list in my previous lecture. So here this is option C is matching, guys. Option C. Okay. So B1 equal to B2 and B3 less than B4. B3 less than B4. Okay. So this is the answer, guys. So I have explained this question now. So I would suggest you for question, please check my previous lecture. I have explained question in detail. Okay, so this is the solution for the question. Last time I was not able to solve that question because of technical error. My class was ended automatically. Okay. Okay, guys. So next question I'm going to solve. Very good question, guys, and very conceptual question from magnetic field. Okay. Next question number 2. Question number 2. Question number 2. Okay, guys. Okay, just give me 1 second, guys. Okay. Okay, guys. Question number 2 is, these are part C questions, guys. Lengthy questions. Okay. Next question is, it's a good question. The state, okay, the the 300, the 3 comma 0 comma 0. Okay, this cat. Okay, this is the state. So 3 comma 0 comma 0 state in the standard notation, in the standard notation, in the standard in the standard notation in the standard notation in the standard notation, that is n comma l comma m. Okay, of hydrogen atom, of the hydrogen atom in the non-relativistic theory, in the non-relativistic theory, in the non in the non-relativistic theory, in the non-relativistic theory decays to the state decays to the state 1, 0, 0. Okay, so this state, okay, so this state decays into this state, okay, via two dipole transition, okay, via two dipole transition, via two dipole, via two dipole, via two dipole transition, via two dipole transition. The transition route, the transition route, the transition route, the transition route, and the corresponding probability, the and the corresponding probability, the transition route and the corresponding probability, corresponding are option number A 3, 0, 0 that decays into 2, 1, minus 1 state, and then it decays into 1, 1, 0, 0, and corresponding probability is given 1 by 4. Okay, option B is, it's a good question, 3, 0, 0, this state decays into 2, 1, 1, 2, 1, 1 into 1, 0, 0. Okay, and probability is 1 by 4. Option C is 3, 0, 0, 3, 0, 0, 2, 2, 1, 0, and this decays into 1, 0, 0, and probability is given 1 by 3. And option D is 3, 0, 0, 3, 0, 0, 2, 2, 1, 0, 2, 1, 0, 2, 2, 1, 0, and probability 2 by 3. Okay, so this is the question, guys. Okay, I'll explain the question first. Okay, after that I'll solve it. So question is the state, okay, the state that is 300, okay, state in the standard notation, that is NLM of hydrogen atom. Okay, for hydrogen atoms standard notation, this is state, okay, hydrogen atom in non-relativistic theory, okay, means in non-relativistic theory means electrons velocity is not relativistic velocity. Okay, so they state this in the standard notation of this of hydrogen atom in the non-relativistic theory decays to the state this. So state 300 that decays in the state 100 via two dipole transition. Okay, via two dipole transition. Okay, the transition route and the corresponding probability are. So you need to find out transition route and corresponding probability. So transition route is like this one. First option is given first it is 300 state, then it goes to 2 1 - 1 state. After that, it finally it goes to 100 state. And probability, corresponding probability is 1/4. And similarly, second option is this state goes to this state via this state, and probability is 1/4. And similarly, the option C is this state goes to this state via this state, and probability is 1/3. And the option is this state goes to this state or decays to this state via this state, okay, and with probability 2/3. Okay, so so now I will solve it for you. Very good question, 5 marks question. Okay, so for dipole transition, okay, via two dipole transition, or for dipole transition, you need to understand for dipole transition, for dipole transition, for dipole transition, for dipole transition, there is a rule, guys. Delta L value is ±1, okay, and delta M value is 0, ±1. Okay, so this you need to note down, guys. For dipole transition, okay, for dipole transition, delta L is ±1 and delta M is 0, ±1. Okay, so this is the rule for dipole transition. Delta L value should be ±1 and delta M value should be 0, ±1. This is for dipole transition, and this dipole transition is happening in this question. Okay. Well, now for if we check all the options, these options, we can see n values are in all options. We can see n values are 2, right? So right, for all options, for all options, for all options, for all options, n is, we can see, 2 in the intermediate state, right? We can, for intermediate state, we can see n equal to 2 for all options. We can see n equal to 2. So value of L is going to be, because n equal to 2, so value of L is going to be 0, 1, because n equal to 2, right? So L value is going to be 0, 1, right? So for L equal to 0, M value is going to be 0, right? And for L equal to 1, value of M is going to be -1, 0, 1. Okay. So for L equal to 0, M value is going to be 0, right? And for L equal to 1, M values are going to be M equal to -1, 0, and 1, right? So, so these are the values, guys. Okay, and in option, all the options we can see the n values are 2. Okay, n values are 2, and so here we can see M. If you talk about L values are, we can see in all the options, that is 1, right? 1, 1. So will not take this value L equal to 0. So L value is 1. For this, we'll solve it. Okay. So the transition, the transition, the transition, the transitions, the state. Okay. transitions, this one 3 comma 0 comma 0, transitions 3 comma 0 comma 0, this goes to 1 comma 0 comma 0. Okay, this transition 3 comma 0 comma 0 goes to 1 comma 0 comma 0, 1 comma 0 comma 0 via, very important one, via 2 comma 2 comma 1 comma m, because we can see here for value of L equal to 1, m values are 3, right? This is minus m, minus 1, 0 and 1, right? And in options you can see for n values this one, right? Okay, so this transition will be via this transition to 1 m, okay, to 1 m, for where for m equal to this one minus 1 comma 0 comma 1 are all value are, for value of m will be this minus 1 comma 0 comma 1 are all valid, are all are all valid are all valid according to the all valid according to according to the according to the according to the dipole transition rule, dipole transition rule, because L equal to 1 means m should be either minus 1, 0 or 1. So this transition will be via this transition for m equal to minus 1, 0 and 1 are all valid, okay, according to dipole transition rule, according to dipole transition rule. Thus there are there are there are three different states, okay. So this one will be means it will go from first 300, then 2 1 m and 1 1 100, right? So m has three values, means three states. One is 301, from 3011 to 21 minus 1 and then 101. Second state is 3011, sorry, 300 to 211100, and third is 300 to 210 and then 100, right? So three transition states, right? So according to dipole transition rule, thus there are three different states. 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 There are three different states through which the state 3 comma 0 comma 0 0 comma 0 state. There are three different states through which this state can decay. This state can decay to this state 1 0 0. So because m has three values, right? So this state decays into this state and then goes to this state, right? So m has three value means this state can decay in three ways, right? So there are three different states through which this state can decay into this state. Okay, each with equal probability, each with equal probability, each with equal probability, each with equal probability. Hence, hence each transition, each transition, each transition has probability, has a probability, has a probability of 1 by 3, right? Has a probability of 1 by 3 because there are three different states, right? That that state can decay. So has probability of 1 by 3. So which option is matching, guys? We'll check it. Option C is matching, guys, because this one 300 is decaying in 210 and then 100 with probability 1 by 3. And other options are incorrect because probability should be 1 by 3, right? So option C is the correct option, guys. I hope, guys, you have understood it. Okay. Next question. Next question. It's a good question, guys, from statistical mechanics. So question is balls of 10 different colors, balls of 10 different colors, 10 different colors, balls of 10 different colors, balls of 10 different colors labeled by different colors labeled by a equal to 1, 2, so on 10. Okay, so 10 different. So there are many balls. There are lots of balls. Okay, of 10 different colors. Okay, labeled by a equal to 1, 2, 3, so on 10. Okay, so one color is represented by 1, second is 2, third is 3, and 10th is 10. Okay, R to be 10, R to be distributed, are to be distributed, are to be distributed, are to be distributed among different colored boxes, are to be distributed, are to be distributed among, are to be distributed among different colored boxes, among different, among different, among different colored boxes, different colored boxes, different colored boxes, different colored boxes. A ball can only, a ball can, a ball can only go, ball can only go, ball can only go in a box of, go, go in a box of, in a box, in a box of, in a box of the same color, in a box of the same color, box of the same color, box of the same color, box of the same color. And each box can contain, and each box can contain, each box can contain at most one ball, contain at most one ball, at most one ball. Let Na, let Na and Na and N, capital Na, denote respectively, denote respectively, denote respectively, denote respectively, respectively the number of balls, respectively the number of balls, the number of the number of balls, number of balls, and the boxes, and the boxes, and the boxes, and the boxes of color A. Okay, boxes, boxes of color A, boxes of color A, boxes of color A, assuming that, assuming that NA, that is number of boxes, okay, with color A, there are 10 different color, okay, so that A can be any one of the color out of 10, among 10 colors, okay. So NA greater equal to NA, NA is the number of boxes is greater equal to number of balls of color A, and this is NA is greater equal to 1, okay. So this is what given. The total entropy, the total entropy, the total entropy, the total entropy in units of, in units, in units of the Boltzmann constant, units of the units of the units of the units of the Boltzmann constant, Boltzmann, units of the Boltzmann constant, units of the Boltzmann constant can be best approximated by, can be best approximate, can be best approximated by, best approximated, approximated, best approximated by, okay. Options are given. Option A is sigma sigma A Na ln Na plus Na small na, small na ln ln Na minus Na minus Na ln Na minus Na. Okay, option B is sigma A Na ln Na ln ln Na minus Na ln Na minus, sorry, this one is plus Na minus Na, capital Na minus small na, into ln Na minus Na. Okay, option C is sigma A Na ln Na minus Na ln Na plus Na minus Na ln Na minus Na. Okay, next option is this is minus. Okay. Option D is sigma A Na ln Na ln ln Na plus Na ln Na ln Na plus Na minus Na ln Na minus Na. Okay, so these are the options given, guys. Okay. Very good question. I will explain the question first, and after that I will explain. Okay. Okay. So question is balls of 10 different colors. Okay, so we have lots of ball, and they have 10, and they are of 10 different colors. Okay, labeled by A equal to 1 to 10. Okay, so one color is denoted by 1, second color is denoted by 2, third color is denoted by 3, and so on. So there are 10 different colors of balls, and labeled as A equal to 1 to so on 10. Okay, are to be distributed among different colored boxes. Okay, so we have to distribute those balls into different. We have to distribute those balls among different colored boxes. Okay, so there are different colored boxes, and we have to fill those boxes, those balls on those colored boxes. But condition is a ball can only go in a box of same color. So there is a condition that ball will go only uh, in a box of same color. If suppose the ball is red, then it will go in red box. If it is green, it will go in green box. Okay. So if so, as per the question, if ball has colored one, right, it will goes on colored one box, not colored two box. Okay, and each box can contain at most one ball. So there is no degeneracy, guys. So in one box there will be only one ball. Okay, the maximum one ball can be in the one box. Okay, not more than one ball in the box. Let Na and small na and capital Na denote respectively number of balls. Na is the number of balls, and capital Na is the number of boxes of color A. So of color A. Okay, suppose if means like the color 2 is there, so Na is the number of so Na and Na are the number of boxes, and Na small na and capital Na are number of balls and boxes of color A. Okay, of color A. So 1 means 1, 2 means 2. Okay, assuming that, and this is important, assuming that that number of boxes of color A are greater than number of boxes number of balls of color A. Okay, A can be 1 to 10. Okay, between 1 to 10, and Na is greater than 1. So this is the condition given. The total entropy in the units of Boltzmann constant can be best approximated by. So we need to find out total entropy. Okay. Okay, guys. So I'll solve it now. So okay, guys. So well, first we will find the number of microstates. Okay. So let n1 ball, n1 ball, n1 balls, n balls of color 1. Okay. N balls of color 1, n1 balls of color 1, of color 1 to be to be distributed, distributed. So n1 balls of color 1. Okay, so n1 balls of color 1 to be distributed in n1 boxes, n1 boxes of color 1, of color 1. So let n1 balls. So there are n1 balls of color 1 to be distributed in n1 boxes of color 1. Okay, so n1 is greater, capital N1 is greater than small n1. Okay, 1. So in that case, omega 1 is going to be this one. So we have to distribute n1 balls, n1 balls of color 1 to be distributed in n1 boxes of color 1, right? So omega 1 is going to be this one. n1c, small n1, right? Or we can write n1 factorial upon n1 factorial upon n1 small n1 factorial into n1 minus n1 capital N1 minus small n1 factorial. Okay, this one. And similarly, n2 balls of color, n2 balls of color 2 to be distributed in ni boxes ni boxes ni boxes of color 2, I mean say n2 boxes, my apologies, n2 boxes of color 2. So there are n2 balls and we have to distribute those balls in n2 boxes. Okay, so then this number of microstate omega 2 is going to be n2 boxes means n2c, capital N2c, small n2, right? So this is going to be n2 factorial upon small n2 factorial into n2 minus n2 factorial. Okay, n2 minus n2 factorial, n2 minus n2 factorial. Okay, and similarly we can write n10 balls n10 balls of color 10 to be distributed, distributed so n10 balls of color 10 to be distributed in n10 boxes of color 10. So in that case, omega 10 is going to be this one. N10C, capital N10C, small n10, right? Or we can write n10 factorial upon small n10 factorial into n10 factorial upon n10 factorial. Okay. So in that case, now, so this means the total and total microstate omega total is going to be this one, n1 factorial upon small n1 factorial into n1 minus n1 factorial plus n2 factorial upon small n2 factorial into capital N2 minus n1 factorial n2 factorial plus so on n10 factorial upon n10 factorial into n2 n10 minus n10 factorial. Okay, n10 minus n10 factorial. Okay, we can write it as total entropy. So total entropy is going to be omega total because these are 10, right? So 10 different colored boxes, and you have to fill those in 10 different colored boxes. 10 different colored balls to 10 different colored boxes. Okay, so we'll add it, right? So this is going to be, or we can write this because this we can add it like this. So omega total is going to be, or we can write sigma A is 1 to 10, right? Sigma A NA factorial upon small NA factorial into NA capital NA minus NA factorial, right? We can write like this because these are the addition, right? 1 to 10, right? So we can write sigma is the color, right? A is the color from 1 to 10, right? So we can write the omega total is sigma A NA factorial capital NA factorial upon small NA factorial into NA factorial capital NA minus small NA factorial, right? So this is this sigma. Okay, this is the number of microstates. Okay, total number of microstates. Now we can find that entropy. So S we know, K ln omega, right? K is the Boltzmann constant. So S is going to be K ln sigma A NA upon small NA factorial upon small NA factorial into NA minus small NA factorial, right? So sigma we can take out. So S is going to be K sigma ln NA factorial upon NA factorial into NA minus NA factorial. Okay, this is the one. Now value of S is going to be, we can use log property here, log property. So this is going to be K sigma A, this is uh, ln NA factorial minus ln small NA factorial minus ln NA minus small NA factorial, right? We have used log property. Log A upon B is log A minus log B, right? This one. Now, so now we will use Stirling formula, right? We know that is approximate formula, that log or ln A factorial or ln x factorial, equal to x ln x approximately, right? This we know. We'll use it. So s is going to be k into sigma A. This is going to be this NA factorial. NA factorial is going to be sigma NA ln NA, okay, minus NA ln NA minus NA minus NA ln NA minus N, right? So this is the answer, guys. So which option is matching? So sigma A NA ln NA minus n small NA ln NA minus capital NA minus small NA ln NA minus N, right? Capital, right? So this is the option, right? This is the correct answer. So which option is matching, guys? So option B is matching, right? Okay, so option B is the correct option, guys. It's a good question. I hope you have understood it. Okay, guys. Okay, guys. So, well, I'm going to stop here, right? And also, guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack exams related to physical science. And also, guys, please share my lecture details with your friends so that they will also be able to watch my free live lectures and will be benefited from it. Okay? Okay, guys. Thank you so much. Bye now.